In science, colours such as red, green and white are regarded as perceptions created by our visual system. Yet they certainly seem to us to be properties located physically outside us in objects and in light. For example, this cup seems to me to have a uniform white colour located in the cup itself and perceived through variations in light and shade. But does this prove that the colour white is actually located in the cup? In this presentation I'll examine this apparent physicality of colour, how it's thought to arise, and the effect it has on ideas about so-called colour mixing in traditional colour theory. I should first explain why I say that in science colours such as red, green and white are regarded as perceptions. The CIE International Lighting Vocabulary, or ILV, is the most authoritative source on the terminology of light and colour in science and technology, and it defines what it calls colour in the perceptual sense, or perceived colour, as a characteristic of visual perception that can be described in terms of 6 specified attributes that are in turn defined directly or indirectly as attributes of a visual perception. Hue, brightness and colourfulness are explicitly defined as attributes of a visual perception, and lightness, chroma and saturation are defined in terms of relationships involving brightness and colourfulness. So colours in the sense of the things we can describe by these attributes, such as white, red, pale pink or high chroma orange, are regarded in the CIE ILV as visual perceptions. But colours are perceptions of something, and the CIE ILV also gives a second definition of colour in what it calls the psychophysical sense, as specification of a colour stimulus in terms of operationally defined values such as 3 tristimulus values. Psychophysical or colorimetric specifications describe what we might think of as the physical property of a light or an object that we perceive as its colour, but more accurately they describe the physical property as far as it is perceivable by the human visual system. For example, our visual system cannot detect the precise spectral composition of a light, but it can detect variations in the overall balance of the wavelength composition of a light at the level of its long, middle and short wavelength components. The colour we perceive as belonging to a light is the way in which we perceive this overall balance of wavelength composition, which is called chromaticity and can be specified on a chromaticity diagram like this one. Newton made this same distinction himself when he said that the rays, to speak properly, are not coloured, but that lights and objects have a disposition to appear this or that colour. Psychophysical or colorimetric measures quantify this disposition to appear this or that colour, and the colorimetric concept of chromaticity can be traced back to Newton's centre of gravity principle that he explained with his famous colour circle. Colorimetric specifications are designed to represent just those physical differences that we perceive as colour differences by ignoring physical differences that are not visible to humans. So, for example, white as a colour of an isolated light corresponds to a whole class of physically different lights, like the 3 on the right, each having a different spectral power distribution or distribution of power through the wavelengths of the spectrum, but having the same chromaticity or overall balance at the level of the long, middle and short wavelength components. These lights would be expected to match in perceived colour when viewed under the same conditions, and in this sense they may be said to have a common disposition to evoke a perceived colour. This matching perceived colour is achromatic or white for an isolated light and under some other viewing conditions, but could vary under other conditions. At the other extreme to white light, the colours we perceive as belonging to the wavelengths of the spectrum are the way in which we perceive a chromaticity that is very strongly biased in a particular direction. Although Newton said that the rays, to speak properly, are not coloured, The rays certainly seem to be coloured. The colours of the spectrum certainly seem to us to be located in the individual wavelength components of the spectrum. But one big problem with this interpretation is that even if the colour yellow was somehow a physical property located in the yellow appearing wavelengths of the spectrum, our colour vision does not work by detecting the individual wavelength components of light and would not be able to determine if these individual wavelengths are present. Our visual system computes the balance of spectral composition of a light at the level of its long, middle and short wavelength components by the process of cone opponency. But cone opponent processing can only determine the overall distribution of power among these three components and not which individual wavelengths are present. The saturated yellow colour that we perceive as belonging to the yellow appearing wavelengths of the spectrum is also evoked by mixtures of longer and shorter wavelengths that completely lack these wavelengths. This saturated yellow colour is a perception not of those specific wavelengths as such, but of a strong bias in spectral composition in the overall direction of those wavelengths. But what about colours of objects? There are two important concepts here. An object colour is the colour we perceive as belonging to an object, and a spectral reflectance is the wavelength by wavelength proportion of light falling on an object that the object reflects, shown by a spectral reflectance curve like the ones on the right. When we can freely examine an object in daylight, this colour we perceive as belonging to an object is the way in which we perceive the overall spectral reflectance of the object, overall here meaning at the level of its long, middle and short wavelength components. So for example, under these conditions, white as an object colour is the way in which we perceive a spectral reflectance that approaches 100% in its long, middle and short wavelength components. Psychophysically, an object's disposition to exhibit a given object colour, such as a particular Munsell hue, lightness and chroma, is specified by the chromaticity and the relative intensity or luminance of the light it reflects under a specified daylight illuminant. For example, a white object reflects light of the same chromaticity and approaching the same intensity as the illuminant. For other object colours, the hue we perceive as belonging to an object is the way in which we perceive an overall direction of bias in the spectral reflectance of the object towards long, middle, short, or long and short wavelengths. The chroma we perceive as belonging to an object is our perception of the amount of this bias in the spectral reflectance, that is, the amplitude of the inequality in the spectral reflectance curve. For example, those cadmium reds, oranges and yellows in the middle rows on the right all have a strong bias, a strong amplitude to the spectral reflectance curve, which we perceive as high chroma. The two earth colours in the bottom row have a weaker spectral bias, perceived as a lower chroma. Finally, the lightness we perceive as belonging to an object is our perception of its total reflectance of all wavelengths, the proportion of the light of all wavelengths falling on the object that the object reflects. So if these were actual objects in the scene on the left, we could be confident from their object colours that their spectral reflectances would resemble the ones shown on the right at this overall level. That is, the spectral reflectance would be about even and approaching 100% for the long, middle and short wavelength components for the white tiles, about even and very low for the long, middle and short wavelength components for the black tiles, and very high for the longer wavelengths and very low for the shorter wavelengths for the high chroma orange cube. Our perceptions of object colour arise so automatically and effortlessly that we have the impression that our eyes directly detect the colours of objects. But this is impossible. We have no direct information about the light falling on objects, so how do we have a perception so closely aligned with the proportion of the light falling on the objects that the objects reflect? let alone the proportion of its three spectral components. What is it that leads us to perceive that there are objects in the distant and shadowed areas of this scene that reflect close to 100% of the light falling on them, when we have no direct information about the amount of that light? These perceptions that seem so direct to us in fact depend on some remarkable unconscious processing. In the words of Frederick Kingdom, our visual system decomposes the visual input into light and material. That is, without requiring any conscious mental activity, it arrives at paired estimates of the spectral reflectance of objects and of the intensity and spectral composition of the light falling on those objects that together are most likely to account for the light reaching our eyes. And it does this so automatically that it doesn't even occur to us how extraordinary this perception really is. In this animation based on Kingdom's Figure 1, notice how the appearance of the scene on the left involves two superimposed perceptions of reflectance and of illumination. We experience these unconscious estimates of spectral properties of the object and of the illumination as a colour belonging to each, respectively an object colour, here a uniform middle grey, and an illumination colour, here a white light of varying brightness. Notice now that over the same rectangle in which we perceived our black, white and high chroma orange object colours, we also perceive a superimposed pattern of varying illumination or light and shade. We might not always be conscious of it, but perception of object colour is always accompanied by a superimposed perception of illumination. Illumination colours are defined in the CIE ILV as colours perceived as belonging to the light falling on objects, which I take to refer to our perceptions of the light falling on each visible object's surface. Illumination colours can vary in the attributes of hue, brightness and colourfulness or saturation, but the illumination here is perceived to be uniformly achromatic or white light, varying only in brightness. This illumination, or light falling on objects, is perceived to derive from two illuminants or light sources, both achromatic, a more intense directional source and a less intense ambient source. The varying brightness of the illumination colours depends on the orientation and location of the object's surfaces relative to these two illuminants. Now notice how these superimposed perceptions of object colour and illumination together account for the light reaching our eyes from throughout the scene. Although they are perceptions, the colours perceived as belonging to the tiles and cube seem to us to be located in these objects and to be seen through the variations in illumination. If our visual system wasn't very consistent in its estimates of spectral reflectance, we would still perceive objects as having colours, but these colours would seem changeable, and we may in fact experience this under spectrally varying illumination, where colour constancy can be noticeably poor. But under varying intensities of the same illumination, the colour we perceive as belonging to an object exhibits a high degree of constancy, and the degree of colour constancy we're accustomed to in daylight is high enough to cause us to think of the stable object colour we perceive through varying intensities of daylight as the seemingly inherent colour of the object. This layered model contrasts with the view of colour vision that I'll call the colour photo or one-layer model of vision, which I've encountered widely among experienced colour educators and other colour specialists. The usually unspoken premise of this model is the seemingly common sense idea that we perceive a single colour at each point in the visual field, like in a colour photograph. If different areas of an object are more brightly or dimly lit, The varying colour appearances are regarded as a range of so-called perceived colours of the object that we could compare by finding coloured chips that match each area when held alongside them. But if we perceive only these different so-called perceived colours in each different area of the object, then what's become of the constant colour that seemed to us to belong to the object as a whole? The colour photo model has led some to talk of this constant object colour as if it was not a perception but a property actually inherent in the object, its so-called inherent, or worse, physical colour. Among others, the colour photo model seems to be behind some claims that we don't really perceive objects as having constant colours, and that colour constancy barely exists. But this is to lose sight of the fact that the object colour is a perception. We perceive it through the variations in illumination. This is a point that can be easier to grasp for the colour novice than for those of us who are long accustomed to thinking in terms of the colour photo model. Following from layered models of colour perception, when we visually perceive objects, we can attend to at least 3 layers of colours. Colours perceived as belonging to objects, colours perceived as belonging to illumination, and colours perceived as belonging to the light reaching our eyes from objects. It's only the colours perceived as belonging to objects, with their attributes of hue, lightness and chroma, that exhibit colour constancy, not the total colour appearance of the objects. Colour constancy in this sense is comparable to other perceptual constancies, such as shape constancy, by which we perceive the tiles in scenes like this as all being square, despite varying viewing direction, and size constancy, by which we perceive such tiles as all having the same size, despite varying viewing distance. In each case, the constancy applies only to the property perceived as belonging to the object, and not to all aspects of the object's appearance. And in each case, this perception of the property belonging to the object arises rapidly and automatically, without requiring any conscious thought from us. Our paired perceptions of object colour and illumination arise so rapidly and automatically that once formed, it can be difficult for us to directly compare the light reaching our eyes from the corresponding areas. Notice in this illustration that we immediately perceive area A as a dimly illuminated bright red and area D as a brightly illuminated dark red. It's very difficult for us to see that the corresponding image areas match, as is shown by the smaller version on the left. If we were to compare the so-called perceived colours of areas A and D by the method of holding up colour chips alongside them, we determine that both areas have the same perceived colour because they both match the same chip. This shows that the light from these two areas would match in isolation, but this is precisely the thing that we don't normally perceive. We can judge consciously that the light from both areas, A and D, is fairly low in brightness and colourfulness, higher in these attributes than from area C, and lower than from area B, and even that both are more similar to C than to B. But it's still hard to perceive that the light from areas A and D matches, because our attention is persistently focused on our paired perceptions of object colour and illumination. In painting, the apparent physicality of colour understandably leads us to assume that the colours of our paints reside in our paints, and so that when we mix our paints, we are mixing their colours. In teaching colour in painting, this can lead to anguish right from the start. One of the first things that needs to be covered is to explore how colours of objects, including paints, can be related to each other in terms of a three-dimensional colour space, which for painters is usually the framework of hue, lightness or value or tone, and chroma. Presented with a hue page like this one shown here, inevitably someone in the class will comment, "I get it, so these are all the colours I can get by mixing that yellow with black, grey or white." Disappointingly, it isn't quite that simple. Mixing paints of a given hue with black, grey or white paints often produces mixtures that drift in hue. In the case of yellow paints, this drift is typically towards green. It is the mistaken assumption that when we mix paints we are mixing their colours that leads us to expect that mixtures of paints should move along straight lines in colour space, and tempts us to blame any disappointment of these expectations on the imperfections of our paints. There are many other examples of departures from the straight line mixing paths to be expected from mixing colours. For example, mixing a value 7 orange paint with a value 7 grey paint might, in theory, be expected to result in a series of mixtures of value 7. But the theory here is again that when we mix paints, we are mixing their colours. In fact, when we mix paints, the spectral properties of the mixtures depend on fairly complex physical processes described by fairly complex mathematics. And the colours we perceive are our perceptions of the resulting spectral properties. To take just one example in detail, we might expect mixtures of quinacridone magenta and titanium white to be a series of tints on a straight line between these two components. But in fact we get a series of mixtures that unexpectedly first increase in chroma before heading towards white, and that shift in hue in the direction of blue. We can understand why this happens if we look at the spectral reflectance curves. We can see from its low amplitude spectral reflectance biased towards long wavelengths that straight from the tube the quinacridone magenta is a dark, fairly low chroma red. Adding some white paint boosts the reflectance of the long wavelengths greatly, the short wavelengths moderately, and the middle wavelengths weakly, making the mixture lighter, higher in chroma, and more bluish in hue. On adding more white paint, the long wavelength reflectance has little room to increase, but the short wavelength component continues to grow, resulting in further shift towards blue. Eventually, the short wavelength reflectance also has no room to increase, and adding more white paint just fills in the valley in the curve, further increasing lightness and decreasing chroma. I'd like to finish with an argument that the idea of three primary colours, red, yellow and blue, that can't be created by mixing, but combined by mixing to make all other colours, has its roots in paint mixing behaviour, viewed from the assumption that the colours we see reside and mix in our paints. My argument involves the concept of the unique hues, which holds that we perceive hues as pairwise combinations of the four unique hues, red, yellow, green and blue, as illustrated in this NCS hue circle. The idea was discussed most famously by Ewald Hering, and his explanation is still a good way of explaining it today. We can all imagine a yellow that's somewhat greenish and a yellow that's somewhat orangey yellow, but in between we can imagine a unique yellow that's neither orangey nor greenish, but just yellow, and we can arrive at unique red, blue and green in the same way. Although firmly accepted for the present in both the CIE ILV and the NCS, the concept of the unique hues does have its critics, including neuroscientist Bevel Conway in his recent review. The impact of this criticism remains to be seen, but I'm myself sceptical of Conway's suggestion that we could think of orange or purple as unique hues as easily as red. It's true that subjects can predict the amount of orange and purple light that you would need to mix to make a red mixture, but that doesn't mean that we perceive red as a mixture of orange and purple. In any case, the unique hues are certainly not just Hering's theory. They appear in the Renaissance in the writings of Leonardo and Filareta, alongside white and black as the 6 simple colours, in Forsius's system of 1611 alongside grey as representing 5 families of colours stretching between white and black, and in the colour nomenclature section of Goethe's Farbenlehre as forming the framework of a 12-step hue classification. And 3 of the 4 unique hues, red, yellow and blue, remain ubiquitous today in traditional colour theory, which I think is all that matters for the argument I want to make. In his very influential book The Art of Colour, Johannes Itten defined the red, yellow and blue primary colours in the same way as the unique hues are defined, except that the primary colours are taken to reside and mix in paints to make secondary colours, including green. This correspondence with the unique hues is also implicit in split primary colour theory, in which the primary colours red, yellow and blue are each placed between a pair of so-called warm and cool versions of the primary, leaning in hue towards the adjacent secondary colours. This double primary theory is very widely used today as a workaround for the fact that a single middle red, middle yellow and middle blue paint mix to form a rather limited and uneven gamut. Traditional colour theorists imagine their warm and cool primary paints as containing the primary colour plus an added impurity or bias of a secondary colour, as in Wilcox's version here, or of another primary colour. But unlike the unique hues, green is classed as a secondary colour made of yellow and blue, apparently based on our experience that mixing yellow and blue paints easily produces a green mixture. Yet if we mix lights of the same colours, we get a white mixture, and if we intersperse stripes of those 2 colours, or if we rapidly spin 2 discs of those 2 colours, we get a grey mixture. So what's going on? What's going on is that it's not the colours that are mixing. These are different physical processes that have different results, and we have different colour perceptions of those results. It's only a dilemma if we think it's the colours yellow and blue that are mixing. When we concluded that green is made of yellow and blue, we were overlooking Helmholtz's explanation from 1852 that paint mixing involves a subtractive process. The yellow and blue colours don't add to make green, but rather the spectral reflectances of our yellow and blue paints share a green-appearing spectral component that preferentially survives this subtractive process. Once we understand that colours are perceptions of spectral properties, it's no longer surprising that combining components having the same 2 colours by different physical processes can yield different coloured results. But if we don't know about Helmholtz and spectral reflectances and subtractive mixture, and if we see a blue paint that visually doesn't contain green, and a yellow paint that visually doesn't contain green, making a greenish mixture, we're understandably led to conclude that the colours yellow and blue have mixed to make green, and so we reject green as a primary colour. This doesn't happen with red, blue or yellow, despite the fact that we can easily make red, blue or yellowish paint mixtures. For example, we can make a red mixture from a magenta and a yellow paint, but the traditional colour theorist can say, no, you haven't created red by mixing. There's already red in the magenta paint, I can see it, plus a bit of blue or violet. What's happened is that we've got some red, yellow and blue, and everyone knows that makes black, and extra red left over, so we got a red mixture that's a bit dirty. And it's true that we can't make a reddish mixture without using at least one paint that's already reddish in appearance. We can mix a violet paint and a blue-green paint to make a bluish mixture. But the same thing happens. The traditional colour theorist can say, no, I can see there's already blue in that violet paint, and we know that green is made of yellow and blue, so there's plenty of blue in that blue-green paint too. So again, we're getting a blue that's already there, plus a bit of black. And again, it's true that we can't make a bluish mixture without using at least one paint that's already bluish. And it's hopeless to say that we can make a kind of yellowish mixture by mixing a yellow, green and an orange paint. For the traditional colour theorist, the green gold already contains plenty of yellow, and orange is made of red and yellow, so the yellow is already there in both and has not been created. And once again, it's true, we can't make a yellowish mixture without one or both components already being yellowish. Explanations of this sort, based on the understandable assumption that the red, yellow and blue unique hues that we perceive in our paints actually reside and mix in those paints, are flexible enough to appear to explain any mixture of paints without disturbing the tenet that red, yellow and blue cannot be made or created or obtained by mixing other colours, and which therefore survives to this day as the characteristic tenet of traditional colour theory. Thank you.